right, today we are talking about statistical inference. So, like before, there is a lot of material here, and just be sure that you are well caffeinated. I got mine right here, so we're going to pop that open. And if you need to pause and take a break, or if you need to reference something in the book, of course, in the classroom you could stop and ask questions. But here, just make sure that you're keeping up with everything. Everything in this section, just like the rest of the class, builds on itself. And so if there's something you're a little bit uncertain of, you really need to stop and make sure that you understand it before we move on to the next section. So recall, one of the most important things we learned last time is thinking about the difference between the sample and the population. And since these are different values, we refer to them differently. When we're talking about statistics, we're talking about what we know from our sample. And we use sample statistics to try to better understand population parameters. And that's essentially what statistics is all about. So we are going to work on statistical hypotheses today. We've talked about hypotheses already. If this happens, then that happens. But we want to try to make some assertions about population parameters. So for example, does the sample that you drew accurately represent the population? Is what you learned about your sample from your survey, from your experiment, whatever it is, can we draw conclusions that we can trust based on the rest of the population? Or we'll talk a little bit today if someone has some hypothesized value of a population parameter, right? That X% of the population approves of Donald Trump or whatever it is. Can we believe that that's plausible? Is it possible? If we have a couple of groups, can we take the average of two groups and can we figure out, are they actually different? Sure, the samples are different, but when we back it out to the population, are they different? And is there a statistically significant relationship between variables? You certainly have heard that term before in classes or maybe in journal articles, statistical significance, and today we'll start learning about what that means. But ultimately, the goal is to find empirical evidence for the hypotheses that you've already laid out. So today we'll be talking about two different types of inferences. We'll be talking about hypothesis testing and point and interval estimation. So again, feel free to follow along in the textbook as we cover some of the material. Not everything we talk about here is talked about in the same detail in the textbook. I do recommend that you start with a lecture video and then reference the textbook as needed. There's a number of things also in the textbook that we just don't have time to talk about here. So hypothesis testing is taking the empirical claims that you've made and trying to translate them in statistical terms so we can test them with statistics and probability theory. Now when we're thinking about hypotheses, and I've mentioned this a little bit in the past, we can't actually confirm a hypothesis. We can't say with 100% certainty that this hypothesis is true. There's always more data, there's always more elections, there's whatever it is. It's very difficult to be 100% certain. Now, we can find all sorts of evidence to support the hypothesis where, for all intents and purposes, it basically is confirmed, in quotes, but technically we can't confirm a hypothesis. So when you have a hypothesis, there's two options. This is just sort of a little bit of verbiage you need to get used to. We can fail to reject a hypothesis, or we can reject a hypothesis. So it's a subtle thing here where we can't confirm the hypothesis, so again, you just sort of have to get used to this language, and we'll talk a lot more about this as we move on, but you can reject or you can fail to reject, all right? We'll also talk about point and interval estimation. Essentially, you're going to have an estimate about some unknown population parameter based off your sample. And then since we know that what you see in your sample might not exactly mirror what's in the population, we're going to surround that estimate with confidence intervals. So perhaps, again, you've heard someone say, we're 95% confident. Well, what does that mean? We'll talk about that. So the first thing I want you to do is go ahead and pause the video, and I want you to write down a hypothesis, your main hypothesis from your research. If this happens, then that happens. If individuals are older, they will pay more attention to politics. if they are more conservative, they will be more in support of President Trump, whatever it might be. So pause, write down that hypothesis, and then come back. All right. So now that you have your hypothesis, what you just wrote down, we like to refer to when we're thinking about statistics as an alternative hypothesis, an H with a subscript A. So the hypothesis you wrote down, we're going to refer to as an alternative hypothesis. Now, when you're doing your write-up, when you're doing everything else, it's your hypothesis. But in the language of statistics, it is technically an alternative hypothesis. One way to think about this is science is always cumulative, it's pushing itself forward. You're proposing through your hypothesis this new way, this alternative way to look at some phenomena of interest or a relationship. So for example, maybe you're doing something related to democratic peace theory. Democracies are less likely to go to war than are non-democracies. So that's my hypothesis. But technically it is my alternative hypothesis. Now for every alternative hypothesis, there is a corresponding null hypothesis, or H sub 0. Essentially, the null hypothesis is the opposite or the complement of your alternative hypothesis. So note the subtlety here. You hypothesize democracies are less likely to go to war with one another. The corresponding null hypothesis is whether or not a country is a democracy has no effect on whether or not a country will go to war. So you think that there is a relationship here. Democracy, less likely to go to war. That's your alternative hypothesis. The null hypothesis is that there is no relationship, hence the term null hypothesis. So you can think about some of the other hypotheses in your arrow diagram as well, but try to take your hypothesis, what you have always known as your hypothesis. We're going to label that an alternative hypothesis, and then we're going to have a corresponding null hypothesis. Now, in your research, in your paper, you don't have to tell me what your null hypothesis is, because I already know what it is. I can take your alternative hypothesis and basically the opposite of what you said, or the complement. So you could say maybe democracies are even more likely, right? So that'd be the opposite of what you're arguing here. So you don't need to write down, here's my alternative, here's my null, because I can piece it together. So again, if this is a little bit confusing, always remember what you think of as your hypothesis has always been your hypothesis. In this case, democracies are less likely to go to war. It just so happens that when we're thinking about statistics, we label that as an alternative hypothesis. And we'll give a lot more examples to sort of demonstrate this. So here is an example. And like I said, we're going to use a lot of quarters over these lectures. And so the null hypothesis is basically the status quo, the idea that the probability of flipping a coin and having it come up heads is 50%, 0.5, 50-50. Now, alternative hypotheses can be of two types. They can be one-sided or two-sided. Sometimes we might say one-tail or two-tail tests. So here are a couple of alternative hypotheses. Again, I'm sort of challenging conventional wisdom, and I'm suggesting that it is not the case that the probability of getting heads is 50-50. So, a one-sided hypothesis. The probability of getting heads is less than 0.5. Or, for the last example, democracies are less likely to go to war than non-democracies. A two-sided hypothesis. Probability of getting heads is not equal to 0.5. So the equal sign with a line through it, not equal to. Probability of getting a heads is not equal to 0.5. Or I could say, with the democratic peace example, the odds that a democracy goes to war is different than that of a non-democracy. So there is a difference between the odds of fighting, but it is just different. So now, take a look at this and see if you can tell what makes something a one-sided hypothesis versus a two-sided hypothesis. Were you able to figure it out? So, the one-sided hypothesis implies direction. So notice here it was less likely to go to war, or less than 0.5. So a one-sided hypothesis would just say more or less or greater than or equal to. The two-sided hypothesis says that there's a relationship, but it does not imply direction. So the probability is not equal to 0.5, meaning it could be higher and it could be lower. It could go on either side, hence two sides. The odds that a democracy goes to war is different than a democracy. It doesn't say it's higher. It doesn't say it's lower. It just says it's different. So one-sided will imply direction. Two-sided will not imply direction. All right, does everyone understand? So with these, you might have the question, well, why do we have this null and why do we have this alternative hypothesis? Remember, with a hypothesis, we have two options. We can't confirm anything. We can reject it and we can fail to reject it. And so what the null hypothesis basically is, that the null hypothesis becomes this straw man. We are trying to reject the null hypothesis, to say the null hypothesis is wrong. And essentially what that means is that there is evidence to support our alternative hypothesis. So we can reject the null hypothesis, or we can fail to reject the null hypothesis. Failing to reject the null hypothesis is to say, geez, we just don't have enough evidence to say that that null hypothesis is wrong. All right, so again, we're going to have a lot of examples of this, but that gives you a little bit of the logic behind why we have a null and alternative hypothesis. So we're going to have our quarter here. All right, so everyone should get a quarter. It's fun to, one of the most fun parts of the lecture in class is watching people try to flip a quarter and see if it comes up heads or tails. But the better part is to see how difficult it is for people to catch a quarter. So let's say that you have a quarter, and you probably think that that quarter is fair. It's just a run-of-the-mill quarter. And so the odds of getting heads or tails is 50-50. But let's say that you flipped a coin 10 times. Under what circumstance would you conclude that that coin could be unfair? So what I do in the classroom is I bring in 10 quarters and I pass them out. And the class trusts me. They have no reason to think that I try to trick them, but they probably don't know me very well. And so I actually suggest to them, there are some unfair coins in this sample. You don't know if you have a fair coin or an unfair coin. So what would you have to see where you would start to be skeptical that that coin is actually fair? So, right, you would expect to get 5 out of 10 coming up heads. But for some people, you might say, geez, well, if I only got 2 heads, I'd start to think this is unfair. Or maybe if I got 3 heads, and then conversely you go to the other side, if I got more than 8 heads, I would think that it's unfair. All right, so basically you're creating this threshold that if this outcome happens, you're going to conclude it's an unfair coin. And if it doesn't come up, you're going to say, oh, no reason to think it's unfair, seems to be fair. All right, so maybe jot down what is the number of heads out of 10, and it could go on the low end or the high end, say, where you would start to say, whoa, this is a fake coin. All right, it's unfair. So the first example I'm going to do here, the null hypothesis, like we said, is that the probability of getting heads is equal to 0.5. That's the conventional wisdom. But I want to test this. I'm skeptical. So now my alternative hypothesis is that the probability of heads is not equal to 0.5. So first off, is this a one-sided or a two-sided hypothesis? I'm not implying direction. I just say it's not 0.5. It might be higher, it might be lower. So it's a two-sided hypothesis test. All right, it doesn't imply direction. So notice here, what I have is I have all the options along the bottom, and I learned how to do a laser pointer here. So it's possible that you can get 0 heads all the way up to 10 heads. All right, now we expect that we're probably going to get 5. And so what this is doing is it's creating this decision rule. All right, and basically I've put together these critical values. If the critical value meaning that if it's on one side, I'm going to do one thing, and if it's on the other side, I'm going to do something else. So there's an outcome for every possible number. If I get 0 out of 10, I'm going to conclude, I'm going to reject the null hypothesis. If it's 1 out of 10, reject the null hypothesis. If it's 9 out of 10, 10 out of 10, reject the null hypothesis. Now, what does that mean? To reject the null hypothesis, we're going to strike this out. Rejecting the null, we're getting rid of it. We're saying there is not evidence that that is the case. And what that leaves us with is the evidence would suggest that we have support for our alternative hypothesis. All right. Now, it doesn't mean that we're confirming the alternative hypothesis. Sure, you know, it again, in quotes, we are agreeing to our alternative hypothesis. But again, in the language of statistics, you can't do that. It's just really rejecting that null hypothesis. What you're left with then is the hypothesis that you think. Now, if I flip the coin 10 times and it comes up with 4 heads, then I fail to reject the null hypothesis. I can't get rid of that. I can't say with any certainty that that's not true. All right? So I created these critical values. Think of the edge of a knife, right? If you're on one side, you do one thing. On the other side, you do the other. So it's very straightforward. We're going to take a sample. We're going to flip a coin 10 times, and we're going to see what happens. Let's see. Do I have a coin here? Let's see. I don't know. All right. I should do this. Just let's see. I said it's funny in class when students try to flip a coin 10 times. And yet, I never do this in front of the students because I could be embarrassed. But it's an online class. You guys are playing along, so let's try it. All right. So I'm going to do it 10 times. All right. Heads. Let's record. So there's heads. 2. 3. All right. 3 for 3. 4. Maybe this is an unfair coin. 5. This is amazing. Oh, there's a tail. 1 tail. Tails. Heads. 2 more. Tails. Alright, I'll try to get a good flip here. I have not dropped it yet. Look at that. Heads. Alright. So, what I came up with here is I have 7 heads, 3 tails. So I go to my chart, and I got 7. And so I conclude I failed to reject the null. There is not enough evidence based off my critical values here to conclude that this quarter is unfair. So, my conclusion was it seems to be a fair coin based off that one sample. All right? So, of course, when we do anything in life, statistics, political science, whatever it is, we don't like to make mistakes. We don't like to make errors. And so notice what I did here is I just took that same graphic here and I condensed it. I put it to the bottom of this slide. And so here's my criteria, right? Now, do I actually know? I mean, you guys just saw me. I took this out of my cup off the desk. I was not planning to do this. It was a spur-of-the-moment thing. Do I actually know if this is a fair coin or not? No. How could I tell if it's a fair coin? I mean, I got 7 out of 10 heads. So, I mean, is it possible that if I keep doing this, that 70% of the time it'll come up heads? I suppose. The one way that I could do this is I could flip this over and over again and just keep recording, right? So it's possible that in the real world, imagine, we'll get philosophical here for a sec, there is truth in the world. Imagine that there is a world where this quarter is fair. In other words, the null hypothesis is true. So look, truth in the real world, null hypothesis, true. In the world where the null hypothesis is true, if I fail to reject the null, essentially saying that the coins are fair, and that's what I concluded. I make the decision over here. I make the decision. I have 2 choices. Reject the null, fail to reject the null. That's all I can do. So in that last example, I got 7 heads. So I concluded fail to reject the null. So I'm living right up here. In the world where this quarter really is fair, and I fail to reject the null, meaning I concluded that it's fair, if that's the case, I've made a correct decision. All right. But now what if I would have rejected the null hypothesis? And again, to reject the null hypothesis is to say that there's evidence that this coin is unfair. So now I'm living down here. I'm rejecting the null hypothesis, but I'm actually living in the world where it's true. In that case, I've made what we call a type 1 error. All right. And now there's a type 2 error as well. It's up in this corner, and you can see what that is. But we're primarily concerned with type 1 errors. That's what we're going to talk about the most. So with statistics, right, we have a sample, and we have to make some decisions based off of our sample. So based off my decision rule down here, I concluded that this is a fair coin. Do we know if we're in this state of the world or this state of the world? Not really, right? We don't know really anything about this quarter. So we always know there's a possibility that we're wrong. Maybe this really is an unfair coin. It just so happened it came up within this range, right? Maybe the next time I flip it, it'll come up 10 heads out of 10, right? And so the goal, of course, is to not make errors. We want to make correct decisions. The problem is we don't really know when we've made the correct decision and when we made the incorrect decision. And so what we have to do is we have to start to think about how much are we okay with the possibility of being wrong, right? When you say that you have a test and there's a penalty if you get the answer wrong. Well, so now you have to say, well, what are the odds I got it right? What are the odds I get it wrong? And is the risk of getting it wrong worth not doing it, right? So we have to think about some of these things. And so we're going to talk a lot about our willingness to make this type 1 error. All right, so make sure that you write down this figure. And again, put a big circle here around the type 1 error. This is what we're most concerned about. When the researcher rejects the null, essentially concluding that there is support for the alternative hypothesis, but in the real world, it's the null hypothesis that's true. So that's making a type 1 error. All right? So here it is written out a little bit, a type 1 error, and it's a little lowercase alpha, looks like a little fish, rejecting the null when it's in fact true. So in the example of the coin, if you say that the coin is unfair when it really is fair. All right, now I included the type 2 error here. I don't want to confuse you. I mean, it's the opposite, so it's not too complicated, but if it helps you to just worry about type 1 error, that's good enough for me. That's my focus. Rejecting the null hypothesis when it is in fact true. So here is our sampling distribution for the 10 coin flips, right? We talked about this last time. So even a fair coin, so let's look at what we did. Here, a fair coin will come up with 7 out of 10 heads. 12% of the time. A fair coin will come up 12% of the time. Now, note it's also possible that a fair coin comes up 0, 1, 2, or 8, 9, and 10, right? Most of the time it's going to be right there in the middle. But it's possible that even a fair coin can be swayed all the way to the left, all the way to the right. All right? So here, this is what my decision rule is. I said that if it comes up 0 or 1, I'm going to reject the null. If it comes up 9 or 10, I'm going to reject the null. But look, this, all the blue, is a fair coin. So here, I'm saying that I'm going to reject the null. But this chart, the sampling distribution, is telling me that it's possible that a fair coin is coming up only 0 or 1 time, 9 or 10 times. So how often would we reject the null hypothesis? Well, we'd reject it if it came up 0 and 1 and 9 and 10. So that's 1.1 plus 1.1. 2.2% of the time we would reject the null hypothesis. But this also means that 2.2% of the time we might be making a mistake because we're rejecting the null hypothesis when in fact it is true. Now, why is it that we chose these values here? This was just my threshold at the beginning. That's what was on the slide. Maybe for some of you, you said, if it came up 0, 1, 2, or 8, 9, 10 heads, then I'm going to be skeptical. So we could change that threshold. So here's what that looks like. So here, how often would we reject the null hypothesis based off this decision rule? For my sample, I still got 7, so I'd still fail to reject the null. But here, you add all these up, and you have 5.5 plus 5.5. 11% of the time, you're rejecting the null hypothesis. But 11% of the time also means it's possible that a fair coin actually falls into this range. So we could be making a type 1 error 11% of the time if this was our threshold. And up here, we'd be making a type 1 error 2.2% of the time. So the question is, are you willing to be wrong 2.2% of the time? Of course, that means that you're right 97.8% of the time. Are you willing to be wrong, what did I say, 11% of the time? Right? You're right 89% of the time. Well, it depends on your threshold, your willingness to accept that risk of being wrong. So when we talk about statistically significant, when we talk about levels of significance, what we're doing is we're saying that the result of a hypothesis test is statistically significant, means that a null hypothesis has been rejected with a specific probability of making a type 1 error. Most of the time, in political science anyways, when we think of our willingness to make a mistake, we're willing to be wrong 5% of the time. Other times we'll report that we're wrong 1% of the time or 10% of the time. And again, like we talked about last time, out of 100 trials that we make, we would make the correct conclusion 95% of the time. If we're wrong 5% of the time, well, we're right 95% of the time. So you really have to think about what level of error are you willing to live with. And in class I talk about, it really sort of depends. Think about if you worked at a light bulb factory. So like Philips or, I can't think of a light bulb company, General Electric. Now, you'd like to think that all of your light bulbs work, but light bulbs I'm sure are relatively cheap to make. I'm sure you get some duds. And so, if I had, $5 worth of light bulbs at home and I had 10 light bulbs and one didn't work, I'd say, man, these were only $5, I don't really care, right? And so maybe for light bulbs I'm willing to make a little bit more error. So now how in the factory they might take samples and say, every hour we're going to go out and we're going to take a sample and we're going to see if the light bulb works. And that's supposed to represent, well, how many of our light bulbs are actually working. Well, that's expensive to do. You need to pay someone to test those light bulbs. And so maybe they're willing to live with 5% of the 5% of the light bulbs just not working, right? And so 95% confidence sounds pretty good, right? 5% wrong, 95% confidence. Well, what about if you went to the doctor and they said, I'm 95% sure that you don't have this terrible disease. I'm 95% sure that you're not pregnant, so you should be good. 95% sure. Well, then you also start thinking about, well, what's the 5% chance that the doctor's wrong, right? You go outside, you have a 10% chance to get hit by a bus. Probably won't get hit by a bus. But man, the consequences are pretty significant if you get hit by that bus, right? So in political science, we like to stick with this 5% chance of being wrong, 95% chance of being right. And we still will report if we're more confident or less confident. We'll talk about that a little bit later. But it helps to have this consistent threshold that is sort of the standard when we're talking about political science. So when we think about levels of significance, stick with that alpha value of 0.05. We're willing to make a type 1 error 5% of the time, which also means that conversely, 95% of the time we're making the correct decision, and so we're 95% confident in our conclusions. So let's stick with that number for now, and I want to go revisit this idea of the one-sided and the two-sided hypothesis test. Now remember, I said sometimes we can talk about it as a one-tail or a two-tail test. So in this here, is this a one-tail or a two-tail test? Notice how it just says the alternative hypothesis probability of getting heads is not equal to 0.5. We're not implying direction. It simply says it could be higher, it could be lower. So this is a two-sided hypothesis. This one implies direction. The alternative hypothesis is greater than 0.5, so it's saying it's in one direction. All right, so that's a one-sided hypothesis test. Now, back before we had this, and remember we had our region of rejection on this side, and we had a region of rejection on this side. All right, that was a two-tail hypothesis, and here you can see the tails of the distribution, so that's where it comes from. So we're willing to be wrong 5% of the time. So we know that region of rejection should cover 5%. So here it's not to scale, but it goes from 0 to 100, and we have a 5% chance of being wrong. Now in this case, all 5% is on one side, on a one-sided hypothesis or a one-tail test. Now what about a two-tail test? We're still willing to be wrong 5% of the time, but when we have a two-tail test, it's possible it could be lower or it could be higher. So our two-tail test has 2.5% in the left or the lower tail and 2.5% in the upper tail. Add them together, you get 5%. So graphically, we can demonstrate a one or a two-tail test depending on where that region of rejection is. Here it's shown a different way with our normal distributions here. All right, so here you have a normal distribution, and this is a two-tail test. There's two regions of rejection, and we have this center of the distribution is our mean. So alpha, in this case, we're sticking with 0.05 or 5%. The area under this curve is equal to alpha divided by 2. 5% divided by 2 is 2.5%, just like you see right here. The area in this shaded region is alpha divided by 2, or 2.5%. Now, in a one-tail test, we're willing to be wrong still 5% of the time. You can see, one, this area is larger. The area under this curve in that region is equal to 0.05. All the rejection region is on one side of the distribution, and conversely, it could be on this side. Would also be a one-tail test, but it's only on one side or the other. All right, and so we're bringing this back full circle when we're thinking about the area underneath the curve. Our standard normal curve we talked about last time. We know a lot about this very special distribution. We know that the mean, median, and mode are equal to 0. The standard deviation is equal to 1. The area underneath that curve, the integral from negative infinity to positive infinity, is 1. We also know something about the area under that curve between different standard deviations. Between negative 1 and 1 is 68% of the data, or 0.68. Negative 2 to 2 is 95% of the data. Plus or minus 3 standard deviations is 99% of the data. Now, just as a spoiler alert here, look right here. We want to be 95% confident. Remember this. Plus or minus 2 standard deviations is about 95% confidence. So we'll come back to that. But again, we're going to use this standard normal distribution to test some of our hypotheses and think about what these critical values are. So one of the things that we do when we do hypothesis tests is we take our data. In this case, it was quarters, right? But maybe your data is the average age of voters. Maybe your data is the ideology of people in your survey, or the quality of life of a country. And what we're going to do is we're going to take your data, like we did previously, and we're going to transform it. We're going to take your data and put it onto the standard normal distribution. And when we do that, what we're doing is we're creating what's called a test statistic. Remember, statistics are about your sample. So we're using your sample, and we're creating a test statistic. Now, there's a formula here. To create a test statistic, you take your sample estimate, a hypothesized parameter, and you divide it by the estimate standard error of the sample statistic. Now this sounds really complicated, right? There's some big words here. It's really pretty simple. You have your estimate, subtract our hypothesized parameter that deals with the population, and then we're going to divide it by this standard error. And here's a formula for that. This lowercase sigma, it has the hat, so that comes from our sample, the standard deviation of our sample, and then n is the number of people in your sample, and that creates a test statistic. Sometimes we refer to it as a z observed, what we're observing, we observe from our sample, and this is when we talk about standardizing, we talk about z-scores before. All right, and then what we do is we calculate this test statistic based off your sample, and then we compare the test statistic to the critical value. Remember with the quarters, we had our critical values, 0, 1, 9, or 10 quarters. We're going to test and do our sample. I flip a coin 10 times, I got 7, and we compared that 7 to what those critical values were. All right, so really for the rest of this lecture, we're going to do a lot of this. Calculate a critical value, compare the critical value to the test statistic. Here's the formula for that test statistic. So now we need to figure out what are these critical values. So the appendix of your book, and every stats book will have this, actually the new addition to the book, I don't really like the table that's in the back of the book. I like one of the older ones. So actually you can go on Canvas and you can download a copy of that appendix, but it's all the same idea. Sometimes you will see what's known as the T distribution, T as in Tom, and sometimes you see a Z distribution, Z as in zebra. In short, we use the T distribution when we have small samples, and we use the Z distribution for larger samples. Both of these look like normal distributions. The T distribution is a little bit shorter and a little more portly, a little huskier there. But because especially we're proposing this thing, we're going to propose to have lots of data, we're going to really stick with the Z distribution. All right. So what I want to do now is we're going to stick with that 95% confidence level, which means we have an alpha of 0.05. We're willing to be wrong 5% of the time. I want you guys, with my assistance, we're going to figure out what is the critical Z value for a two-tail hypothesis test, or the critical Z value for a two-sided hypothesis test. And then next I'll want to figure out the critical Z value for a one-tail hypothesis test. All right, and so we're going to use this chart to help us out. This is what the chart looks like that you'll download on Canvas. The one in the book doesn't have this figure here, but you'll note that right here, it's a normal distribution, right? We've seen those, we've been talking about those. 0 is right there, so here's our standard normal distribution. Now this one is labeled standard normal probability in right-hand tail, so we're looking at this tail. It says for negative values of Z, probabilities are found by symmetry, which is a simple way of, or a more complicated way of saying rather, that this chart is only showing us one tail. All right. So our first thing is we want to do a two-tail test, 95% confidence. Now the problem is this chart is only showing us one tail, and here's our Z. And it's a little bit tough to see on the screen here, but this region here is shaded in. And what this chart is showing us is it's showing us the area. This is a whole chart of area, the area of that shaded region. And so as Z moves in this direction, that shading area gets larger, and therefore the area underneath that curve is larger as well. So we know from the standard normal curve that the area under the entire curve is 1. All right. We also know that because it's symmetric, the area under half the curve, all on this side, is equal to 0.5. So now, the way that you read this chart, and there's a bunch of different versions of this chart, but it's all the same idea. Once you figure out one, you can figure out the other ones. Here we have a Z-score, and we're going to start by looking at this column, and we're going to have, these are all the z-scores, so 1.0, 1.5, 2.0, and then you also have a second decimal place. So for example, if you were looking for the z-score of 0.55, you start here, 0.5, and we're going to go over here until we get to 0.05, so 0.55, the area of that region, or the probability here, is 0.212. So if z was right at 0.55, the area under that curve would equal 0.2912. Alright? So what we want to do, remember from before, this is a two-tailed test, 95%. We're willing to be wrong 5% of the time. Now, we're going to start with a little of a trickier one here, because the area in a two-tailed test of this one tail, it's not 5%, it's 2.5%, right? Because there's 2.5% here, and then there's 2.5% here. So what I want to do is I want to find on this chart, we're going to look in the inside of the chart, where is 2.5%, or in decimal form, 0.025. All right? So take a look at this chart and try to find where you find the decimal place 0.025. And from that, we want to figure out what our critical value is. So I'll let you take a look there. All right. So the area here is 0.025, or 2.5%. And if you found it here, here is your 2.5%. So what is the corresponding z-score to 2.5%? We start over here, 1.9, 1.96. When this shaded area is 0.25, z is 1.96. And then by symmetry, over here, negative 1.96, the area there is 2.5% as well. So they add up 2.5%, 2.5%, 5%. All right. So the critical value for a two-tailed test with 95% confidence is plus or minus, because it's on either side of the y-axis, plus or minus 1.96. All right, let's do the same thing with a one-tailed test. Now this one is a little bit easier because we're only looking at one tail, so the picture helps a little bit. So now you need to figure out where on the chart, what's the z-score, and now the area is 5%, or 0.05. So you need to find 0.05 in this chart and then find the corresponding z-score. So take a look there. Here's our 5%. Now this one's a little bit tricky because the chart is not specific enough to give you exactly 0.05. But many of you probably found it right here. So here is 0.0505 and 0.0495, meaning that 0.05 would be right in between these. So the critical value here is 1.6, and then halfway between these numbers, 1.645, right in between those. All right? So in the end, we have our t and our z distribution. Again, we're sticking with that z distribution we talked about. For 95% confidence, 5% chance of being wrong, our critical z value for a two-tailed test is 1.96, and that's on positive and negative because it's two-sided. And the critical z value for one tail is 1.645. Now, if you're really curious, those values, if you were to use that t distribution, and there's a t distribution in your book as well, for the same probability of being wrong, the critical values are a little bit different. But again, one of the nice things about sticking with the z value, especially the first time you're learning this, is we're going to have the 95% confidence level, 5% chance of being wrong. Your two-tail critical value will always be 1.96 plus or minus, and for one tail, 1.645. And so once you know this for the standard normal curve, we really don't need that chart anymore. When I hand those out in class, I really want like students, once they figure this out, to tear up those charts, to like be symbolic about like once you use the standard normal curve, the rest is easy, which is one of the reasons we use the standard normal curve. But I don't want to waste, I guess, that much paper. But again, these are numbers worth memorizing, right? This section right here. 1.96 for the two-tail test, 1.645 for the one-tail test. So recall that we did this with the quarters and we just set our own values. So we had critical values for our quarter game. But the problem is we had critical values for the quarters, and if we would have done a different variable, if we would have done ideology or age or height or weight, we could also come up with critical values, but they would be different every time. The nice thing about the standard normal distribution is it has consistent critical values. If we take whatever data we're working on, everyone in this class is looking at different distributions and different variables. But everyone can transform through that calculation of the test statistic, can transform that and put it onto the standard normal curve. And the standard normal curve is great because we know what the critical values are. It doesn't matter what variable you're using. Once you put it on the standard normal curve, and we agree that we want to be 95% confident, meaning we're willing to be wrong 5% of the time, these are your critical values. So here is a two-tail test. I said before, we're going to really, for the rest of this lecture, compare the test statistic, which we calculate from our sample, and compare it to the critical value. All right, so here's a two-tail test. Two-tail test. We're willing to be wrong 5% of the time. Alpha is 0.05, which means we're 95% sure, and here are our critical values. Negative 1.96 over here, 1.96 over here. So all we're going to do is we're going to calculate a test statistic, and then we're going to plot it on this chart. If the test statistic falls right here, we're going to reject the null hypothesis, right? This is where that shaded region would be. We reject it. Over here, we reject the null hypothesis. In the middle, we fail to reject the null hypothesis. And here is that written out mathematically. If the absolute value of the test statistic is greater than or equal to the critical value, reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So it's the same thing we did before, it's just written out mathematically. And because it's a two-tail test, we can take the absolute value, which basically means using a positive number. If the z that we observe as a positive number is larger than the critical value, so if we observe 3 is larger than 1.96, we reject the null. If what we observe is not larger than that, meaning it's in the middle, we fail to reject the null. All right? So it's very straightforward. With a two-tail test, if it's in the middle, fail to reject the null. On the outside, above the critical value or below, reject the null. Right? And recall, rejecting the null means we get rid of that null hypothesis, and what we're left with is support for our alternative hypothesis. Here's the one-tail test. In this case, the one-tail test is in the positive direction, right? Here's our critical value that we found before. One-tail test, 95% confident. We're willing to be wrong 5% of the time, right? If it's in this region, we reject the null. If not, we fail to reject the null. Here, the decision rule is if the absolute value of what you observe is greater than or equal to the absolute value of the critical value, reject the null. Otherwise, fail to reject null. So it's the same thing. If you get a 3, reject the null. If you get a -1, fail to reject the null. If you get 2.5, reject the null. Anything else below that, fail to reject the null. Right? So it's very straightforward. We calculate a test statistic, we compare it to the critical value. We know what the critical values are now, so long as we stick with that standard normal distribution. We know the difference between a one or a two-tail test, and we're willing to be wrong 5% of the time. All right? In In Canvas, there's a link where you can download just some blank normal distributions. I'm terrible at actually freehanding these. So what you can do then is take these two slides and you can make note of it. So this is more helpful as you're studying, right? And you can shade in. Where do you reject the null? Where do you fail to reject the null? Use green and red if it helps. Break out your colored pencils and get artistic here. So now let's get to some example. So imagine that in a recent article there was a claim made that UNCW students spend 4 hours studying per week for each class that they take. Let's just think about that for a second. So that means if you take 5 classes and you study for each class 4 hours a week, that means you're studying 20 hours a week. When I say this in class, there are some chuckles initially, right? It seems to me that when people laugh at this, the reason they're laughing is they say, wait a second, here's this class. Am I studying 4 hours every week outside? Now, maybe for the test, but this is just the average week, right? Now, for a summer online class, this is a little bit different, right? But and so the null hypothesis is really what this article claimed. They're saying that UNCW students, that's our population here, studied for 4 hours. But the students are laughing at this. They're saying, wait a second. They think the hours studied are less than 4. They don't believe the newspaper. So the first question is this a one-tail or a two-tail test? A two-tail test would not imply direction. A one-tail test does imply direction. And based off the laughter from in the classroom, students seem to think that there is a directional hypothesis here, that students are studying less than 4 hours for each class that they take. So this is a one-tail test. As soon as you determine it's a one-tail test, we're going to jump to this figure. Here is our one-tail test. Because it's less than 4, we're putting the critical value on the left-hand side. This is a one-tail test. We're willing to be wrong 5% of the time. The critical value we know is negative 1.645. So immediately now what we're going to do is we're going to calculate a test statistic, and we're going to see, based off our sample, does the test statistic fall in the region of rejection, or does it fall in the fail to reject the null? All right? So you read this little story problem, you find out it's a one-tail test, and this is what you're thinking about. So we're going to calculate that test statistic. Now this, I'm not going to ask you to calculate something that's difficult. I'll do the math for you. But based off our sample, we sampled, and we have a sample of 46 students. And I calculated, maybe I just used it in Excel, I calculated the average hours that these 46 people studied were 2.91 hours. So that's our X bar. That's our sample mean right here. The hypothesized parameter about the population, that's where we use mu, the newspaper said it was 4. So here is 2.91 minus 4. Now we have to do the standard error here. The standard error is simply the omega hat, or the standard deviation based off sample, and this is something I could calculate in Excel. So I got 1.99, and I surveyed 46 people. So if you have a formula, and if you plug in those numbers, and if you're good at using a computer or a calculator, you can do this math. 2.91 minus 4 is equal to negative 1.09. Do this division problem, take the square root of it, 0.208. You do that math, and the test statistic from our sample, this is a sample statistic, is negative 5.24. So negative 5.24. We're going to take that number we just calculated. We're going to go back here. Where on this line is negative 5.24? It's not even on the graph. It's so far this way. All right, so maybe it's over here. So when that point is here, is it in the region of rejection? Is it beyond the critical value? You could do it this way. Is the absolute value, so you're making that number positive, is that greater than the absolute value of this? Is 5.24 greater than 1.645? Yes. When that is the case, you reject the null. Remember, this was our decision rule, which was the complicated or more mathematical way of saying, look at the picture, which region is it in? In the one-tailed test, over here is where you're rejecting the null. Over here is where you're failing to reject the null. 5.24 is way beyond, in this case, the negative critical value. We reject the null. So what does that mean? What does it mean substantively? Statistically, yes, we reject the null. Substantively, what does it mean? We're rejecting the null hypothesis that the newspaper says that the average UNCW student studies 4 hours. Based off of our sample, the odds that our sample is drawn from a population where the hour really is 4 is extremely low. It's all the way over here. Think about that quarter example. The odds, what is the area under the curve beyond that 5.24? It's extremely low. Now, we might say maybe we just have a bad sample. We have a group of students that don't study. We went to the bar on a Monday night and we asked those people how much they studied. But based off a truly random sample, if we get that number, that 2.91 hours, and the newspaper claims it's 4 hours, the odds that we drew that sample are extremely low. The odds that we make a mistake are far lower than the 0.05 that we're willing to, so we reject the null hypothesis. And we conclude that UNCW students study less than 4 hours per class that they're in. Now, let me just dial back for a second. Here's a normal distribution. We said that every normal distribution has the characteristic of you have a mean in the center, and then between the mean and one standard deviation, that's the sigma there, it's 68% of the area. 95% of the area is between plus or minus 2 standard deviations. 99% of the data plus or minus 3. So what does that look like in our example here in the study? So here, the paper said that it was 4 hours studied as the population parameter. So if we put that in the center, we could then take our standard deviation, which was 1.99, and we could label this 4 plus, so that would be 5.99. This would be 5.99 plus 1.99, and we could do the math in the other direction, right? So we can have a normal distribution of the hours studied at UNCW. We could also have a normal distribution. Maybe this is the average age of, I don't know, people in a wine bar. I don't know. The average age is about 55. So we could figure out our critical values here, plus or minus those 2 standard deviations. This one is a little bit more spread out, right? So we could find the critical values for any normal distribution. The problem is every unique normal distribution will have a unique set of critical values, so it makes it a little bit more complicated. But when we use that standard normal distribution, when we take your data about shoe size, about political ideology, about quality of life, about the unemployment rate, whatever it is, if we take that data and we transform it by calculating a test statistic onto the standard normal curve, we immediately know that these are the critical values for a one-tail test, for a two-tail test. So again, the standard normal distribution, it standardizes things, hence the name, and it helps us calculate these in a much more efficient and systematic way. So what if that article said that it wasn't 4 hours that the average student studies, it's actually 3 hours. So here everything else is the same. The difference is now that mu is 3 hours. We're going to plug in all those numbers, and now the test statistic, we'll do all the math. The test statistic we calculate is negative 0.43. Well, that's quite a bit different than before. Now we're still using this picture here, our one-tailed test. Here's the critical value. Where is negative 0.43? That's probably about there. Now we could also take the absolute values and say, okay, so is the positive version, is 0.43 greater than or equal to 1.645? No. And when it's no, we fail to reject the null. Based off the hypothesized population parameter that the newspaper said, in this case 3 hours, and based off our sample, which came back at 2.91, we cannot conclude with 95% confidence that the newspaper got that number wrong, right? Our sample is too close to what the newspaper said to say that the newspaper was wrong, right? So in this case, we fail to reject the null because that population parameter that the newspaper said was different. You can also do this same sort of thing with proportions. Proportions as sort of like a percentage, right, between 0 and 1. So according to the UNCW paper, this time a mock election a few years ago had Senator Burr winning re-election in 2016 with 40% of the vote. So that's just a sample of UNCW students. So the paper is hypothesizing that the probability is 0.4. That's what we expect him to get on election day. Now, someone might say, geez, I'm not sure if that's right. I think it's different than 0.4. Now notice they don't say it's higher or lower. They just say it's different. Maybe it's higher or maybe it's lower. So this now is a two-tail hypothesis test. There is a formula to calculate the test statistic. The formula is a little bit different, but it's the same idea. And if you have a formula and you figure out what the numbers are, you can plug in those numbers. Now, the critical value, it's a two-tail test, is plus or minus 1.96. We're going to calculate a test statistic based off that past formula, and we're going to see where it falls. If it falls out here, we would reject the null and conclude that the newspaper was wrong. If it's over here, we reject the null and conclude the newspaper was wrong. But if it falls in between, we don't have sufficient evidence. We fail to reject the null hypothesis. We cannot say, based off of our sample, that there's enough evidence to say with 95% certainty that the newspaper was wrong. So let's see what happens. We did a survey, and based off our survey, we got the number 45.5% of students were planning to vote for Richard Burr. So as a proportion, that's 0.455. So let's calculate that test statistic. This is based off of our sample. That's the 0.455. The newspaper said the true value is 0.4. Down here, we just follow the formula. Here's our 0.455, 1 minus that value. We interviewed 46 people, subtracted by 1. You can do all this math if you had a calculator, if you had a computer. Our test statistic is 0.743. We go back to our chart. Where is 0.743 here? It's right in here. And at this point, you should recognize that's right in between our critical values. And when you're in between the critical values in a two-tail test, you fail to reject the null. We cannot conclude that the newspaper was wrong. All right? So now, we can also think about this, and we can calculate confidence levels and then intervals. We can take that, hey, we want to be 95% confident, and we have an estimate based off our sample, and we want to surround that estimate with some interval, that we're 95% confident the true value is somewhere in that range. All right, so this is that point in interval estimation that we talked about earlier. So again, the sampling distribution that we use when we're trying to figure out this confidence level. We've already decided we feel pretty good with being 95% confidence. All right, so here's a formula. This is a formula that would be worth remembering. To create this 95% confidence interval, we're going to take our estimate. This is based off our sample. Take our estimate, plus or minus. Remember, because plus would give you one boundary and minus would give you the other. The standard error multiplied by the critical value. Now, if you remember the order of operations from math class, I really should have some parentheses here because you're supposed to do the multiplication first. So in your notes, make sure that you have some brackets or parentheses here. First, you multiply the standard error times the critical value. You take the answer to that, estimate minus this, estimate plus this. But again, you do the standard error times the critical value first. We always do multiplication first. So let's take that, we'll do a little bit more modern senator here. We'll do Senator Tillis this time, all right? So here, our estimate for Tillis, I want to show our love to both North Carolina senators here, 0.455. The standard error, I circled it down here. It's just the bottom part of that test statistic equation. So there's your standard error. Now the question is, what's our critical value? Well, a confidence interval has two sides to it. All right, there's a higher end and a lower end. Also, just like you have in a two-tailed test. So what's our critical value for a two-tailed test? 1.96. So now you take the estimate plus standard error times a critical value, estimate minus the standard error times a critical value. Mathematically, you can lay this out, calculate it out, and so the higher boundary is 0.6, the lower boundary is 0.31. So based on our sample, we can be 95% confident the true support for the senator at UNCW is between 31 and 60%. Now I'm just switching back and forth between Tillis and Burr, but they're both white male senators from North Carolina, so at that point we'll just count them as the same. So again, here's the formula that you would do to calculate that test statistic before, but we can also decide if we have a range around that estimate. So this is our point and interval estimate to create a 95% confidence interval. Now, if I get contacted by the news and they ask me for my take on the prediction for the election, if I said, I'm 95% sure that the true outcome on election day will be Richard Burr getting somewhere between 31 and 60% of the vote, that's not really a hot take to say that, man, there's a 30% range that the true value could be in. Donald Trump might win the election, Donald Trump might lose the election. Not really, again, really confident there. So the question is, why is that range so large? Why is it that it's between 31 and 60%? Well, remember our survey only asked 46 students. If we asked more people, if we had a larger sample, our estimate would still be the same, but that interval would start to shrink down. Remember, the larger the sample, the less variation we have, the smaller that standard error. We talked about that with the sampling distribution. So here, a larger sample, if we still predicted he would get 45.5% of the vote, that interval would be a lot smaller. All right, now let's look at another example here and create a confidence interval, this time using an Obama feeling thermometer. So in our survey data, we have, there's a total of 46 participants. You can see that right here in the standard error calculation, 46. The average feeling thermometer was right about in the middle at 51.6, and the standard deviation was 30. Now, if you recall the equation, the estimate plus or minus the standard error times the critical value, we need the standard error. So this is the formula for the standard error that we saw before. Again, you're just plugging in numbers here. You don't need to memorize the standard error formula. So 30, the standard deviation, divided by the square root of the number of people in the survey. So the standard error is 4.42. So we plug everything into our equation here. Remember, we need to do the standard error multiplied by the critical value first. So our standard error is 4.42 multiplied by the critical value. Again, this is a two-tail test, so the critical value with our 95% confidence, 5% chance of being wrong, is 1.96. So we do our estimate plus this calculation, the estimate minus this calculation, and this is our confidence interval. We're 95% confident that the true value, the population parameter, is between approximately 43 and 60. So again, though, because of that small sample size, only 46 people, it's a very wide confidence interval. So I want to show you now what happens if we start to boost the size of that sample. So here is just a table I put together. Here's what we just did. This is the sample of 46. There's our standard error. This is the lower end of the confidence interval. This is the upper end, and then this is the width. So there's a 17.3 unit wide confidence interval. So it's pretty large, right? You're not going to really impress many people who say, hey, geez, I think it's between 43 and 60. If we were to double the sample to be 92, now notice the average is still the same. We can even say that the standard deviation is still the same, but the standard error starts to decrease because that sample is getting larger. Now, the confidence interval is between 45.5 and 57.7. Now, if we really make a larger sample and increase that to 500, Now look at how small the standard error is. Again, even if the average and the standard deviation stay the same, just because that sample size is going up, the standard error is going down. And now, to say that the range of this confidence interval is 5 degrees wide is much more accurate, and you can be much more confident about your estimate compared to a sample of that's 46. So as that sample size goes up, your standard error goes down, and you're more confident that something that you draw from that sampling distribution is going to more accurately represent what the population parameter might be. So here I can show this in another way. Let's say that someone claimed that the Obama feeling thermometer for UNCW was 55. So here we'll plug this in. This will be our null hypothesis. And you say, no, I don't think that that's quite right. Well, we can test that. Here's our alternative hypothesis. This is a two-tail test because we're not saying which direction it is. So we can use the confidence interval to test whether or not it's possible that the true value is 55. Now what I did here, and this might help you if you picture things a little bit better graphically. Here are our 3 examples, 46, 92, and 500. This red line here is the confidence interval for 46, 92, and 500. So the confidence interval is more compact as soon as you increase the sample size. Now here in green is our null hypothesis. So if we're 95% sure that the true value is somewhere in this, skip that, somewhere in this range that also contains the null, then we can't exactly say that the null is rejected. So the rule of thumb here is if the confidence interval does not contain the null hypothesis, then you can reject it. So in this one, we fail to reject the null. In the 92 sample size, we fail to reject the null because there's 55 right there. And in the final one, the 500 sample size, here, the null hypothesis is not part of the 95% confidence interval. So we're 95% sure it is not there, and that's what we're willing to be wrong 5% of the time. And so if you would imagine even the normal distribution kind of drawn right there, this is all the way over in a tail. So if we draw this sample and we're 95% sure the true value lies in here, that tells us that the odds that the actual population parameter is 55 is much smaller than the 5% error we're willing to make. So here we can reject the null. So even though the average standard deviations stay the same, the size of our sample really has an impact on what we can do statistically, right? The larger the sample, the more statistical power we have to have confidence in our conclusions. So far what we've been doing is we're taking a sample mean and we're comparing it to a proposed population parameter, or we're creating an interval around one of our estimates. So now we'll take a breath, and next we're going to use statistics to test relationships between variables, or perhaps compare one mean to another mean. All right, so the first test that we'll look at is known as a difference of means test. So imagine that we have a population that we care about, and we have a sample. Now this time what we're going to do is we're going to take that sample and we're going to divide it in half. Think back to doing experiments. Here you randomly divide the sample in half and you have a control group and a treatment group. Or maybe we're curious about how males compare to females. Or we're curious about the issue positions of Democrats versus Republicans. So we're comparing two groups. And for each group we might have an average score. And so what we're doing now is we're trying to compare the descriptive statistics of two groups within that sample. So for example, thinking about that Obama feeling thermometer, is there a difference between how males rate Obama on that feeling thermometer and how females rate Obama? So this is a difference of means test. So where does that name come from? So let's use the experiment as an example. The experimental effect is really the difference between the treatment group and the control group, right? So you give someone this medicine that's supposed to help lower blood pressure. So you compare the average blood pressure of the treatment group with the average blood pressure of the control group. Any difference that's there is the experimental effect, which you can contribute to the treatment. And so with the difference of means test, here you have a null hypothesis, and you have an alternative hypothesis. So look over here on the left. The null hypothesis is that the average effect of the treatment is equal to the average impact of the control group. Really, so there's no difference, right? That regardless of if you took that drug, the drug doesn't impact your blood pressure. The alternative hypothesis is that there is some difference. So the treatment effect is different than what happens to people just in the control. So saying that they're equal to is the null, that they're not equal is the alternative hypothesis. Now, alternatively, you can do this even if you do a little bit of algebra, and basically all you're doing is you're moving this to the other side. The null hypothesis, you could also write the treatment minus the control. If those two things are equal, taking the control away from the treatment will result in a 0. The difference of means, hence the name, would be 0. That's the null hypothesis. If there is a treatment effect, you would expect that the treatment minus the control is not equal to 0. All right? So that's where the difference of means comes in. But again, you're most likely to see this when we're doing things like experiments or comparing to two different groups. So just like before, we're going to calculate a test statistic, which is the observed difference that you see between the control group and the treatment group divided by the standard error. And you'll take this test statistic and compare it with a critical value, which is a two-tail test. So that critical value is the 1.96 because we have the not equal to here. All right. Now, this formula is a little bit more complicated, but you don't have to memorize this formula. I'm not going to ask you to calculate this formula, but I just want to demonstrate that once you know what the formula is, you could plug in these numbers, and if you had a calculator or computer, calculate them. So here there's two samples, hence you have the number of cases in the first sample, say the treatment, and the control, the sample variance for the treatment and control, the sample means for the two, and here is one method, so when the variances of the two samples are equal. Again, it looks pretty complicated, but if you just break it down and plug in the numbers, it's relatively straightforward. Here's another method if you have variances that are unequal. Again, you don't need to memorize this stuff. This is just showing you that there is a formula to do this, and if you really sat down, you could plug and chug and work your way through this model. You can also do a difference of proportions test where you have, 40% of this group believes this, 40% of the treatment group believes something else, and so you can see the difference between those proportions. Same deal as the difference with means. Your null hypothesis is that there's no difference, or the difference is equal to 0. The alternative hypothesis is that there is a difference. Still, all you do, calculate a test statistic, compare with a critical value, and determine whether or not you reject or fail to reject the null hypothesis. It's the same procedure. It's just a matter of looking at the data, trying to figure out what it is that you need to analyze, and deciding which test is the most effective to understand the relationships that you're trying to explain. So now let's dial it back a little bit, and let's start thinking about just some simple relationships. I talk about sports quite a bit, and so one of the questions in the survey that I ask deals with what is your favorite professional sport. I really like college sports. Professional sports are good, of course, too. And so here are some results. Here we have 45 people that answered this question, and this is a basic frequency table. 5 people said they like Major League Baseball, 11%. 20 people said that they like the NFL, some Carolina Panthers fans in there. So we have a couple of different sports represented, and all those percentages add up to 100%. And so I'm curious, if we wanted to predict, science is predictive, what is someone's favorite sport? Is there a way to do this? What would we want to know about someone to predict their favorite sport? All right. Well, what if could I use gender to predict someone's favorite sport? And so now what I did is I had asked people their gender in the survey. And now what I've created is known as a cross-tabulation. Up here is it's a tabulation. I'm tabulating how many people, what percent said which answer. What I'm doing here is taking the favorite sports, and if you note, 5, 8, 20, 3, 5, 4 is exactly the same thing that you see right here. 5, 8, 20, 3, 5, 4. The difference is now I'm splitting the people that said Major League Baseball by whether they said female or male. And so in total of those 45 people, 21 females, 24 males. And so now this is a cross tabulation. I'm essentially taking two variables and I'm crossing them into this grid here. Now when we do these tabulations, sometimes it's more useful to explain things as a percentage, right? To say how many points you got in an assignment, while it varies based off how many points were possible. But to say a percentage, you got a 95%, that means something a little bit more concrete. So it's possible that depending on how we calculate the percentage, you can say two different things here. We could look at row percentages and what are known as column percentages. So remember, our columns are up and down, like the columns on a building, and our rows are left to right. So this 14% here, when you're thinking about row and column percentages, you really need to find where is the 100%. In this case, it's over here. On a row percentage, the 100% is at the end of a row. In a column percentage, the 100% is at the bottom of a column. So 14% of females, because that's where the 100% is at, 14% of females like Major League Baseball the most. Compare that to here. 60% of the people that like Major League Baseball are females. And so you're saying two different sentences really about the same number here, depending on how you calculate the percentage. Is it 3 over 5? That's the 60% down here. Or is it 3 over 21, which is the 14%? Again, row percentages have the 100 at the end. Column percentages have the 100 at the bottom. Sometimes you can say this and you can sort of figure. So let's do it backwards here and do it the incorrect way. This is the incorrect way. 60% of females like Major League Baseball. Well, if that were true, 60% of females like Major League Baseball, 63% of females like the NBA. Well, this is all going to add up to way more than 100, right? You want your percentages to add to 100. So the correct way, 60% of those who like Major League Baseball are female. Or let's go up here, 5% of females like the NHL. Right, so row versus column percentages. Well, let's look at animals here. We already concluded that dogs are more popular than cats, and this shows us we have 82% of this particular sample says that they prefer dogs to cats. So I wonder if we could predict whether someone likes dogs or cats based off another variable. We'll try gender again. So here we have our frequency. We split up our 45 participants by male, female, and then dog and cat. So here we have 3 people that are female that prefer cats, 5 that are male and prefer cats, so on and so forth. So again, we can do row and column percentages when we have these cross tabulations, or sometimes we just call them cross tabs. So here, I'll point to the number and tell me, think of the sentence that describes this, all right? So circle this 86%. What does that 86% mean? Come up with the sentence on your own. So you first need to determine where the 100% is at and use that when coming up with the sentence to describe what's going on here. So 86% of females prefer dogs. 79% of males prefer dogs to cats. Now we can look at the column percentages. 49% of dog lovers happen to be female. 51% of dog lovers happen to be male. So the question is now, is there a relationship between gender and favored animal? And now, before we looked at the data, you might have had an idea about this and say, hey, females like dogs, guys like cats, vice versa, or maybe there's no relationship. And so we're testing statistically, is there a relationship here? Now, one of the things when we do this, we're not necessarily looking at, is there a causal relation? We're not saying that gender causes one to like one animal or the other. but rather, is there some association here? Is there some relationship? Do they depend on each other in some regard? Well, just by looking at these numbers, based off this, would you say that whether you like dogs or cats really depends on gender? As you can see, I mean, it's pretty much the case that dogs are just more popular with both groups, right? 86% of females prefer dogs, 79% of males prefer dogs, right? If there was a relationship, you might expect that, say, maybe there's a much bigger number here for females and a much bigger number here for males, or vice versa. But perhaps we can be a little bit more certain and concrete than just saying, it kind of looks like there's a relationship, or maybe there's not. What about this one? Here I have a cross-tabulation between party identification and who survey respondents blame for the state of the economy. Now, when I asked this question, it was several years ago when President Obama was president, and some people thought that it was dysfunction in Congress that was resulting in a sluggish economy. Some people said, well, it's all the work that George W. Bush did. Other people said, well, it's President Obama. Is there a relationship between an individual's party identification and who they blame for the economy? Now, it probably is not surprising. You might hypothesize that Democrats are going to be more likely to blame George W. Bush, who was a Republican president, and Republicans are more likely to blame Obama. Well, we can look at this. First place to start is to consider these row and column percentages. So just like what we talked about, find where the 100% is over here. 100% of strong Republicans blame President Obama for the state of the economy. Conversely, 83% of strong Democrats blame George W. Bush. Of the people that blame Obama, 56% are Republicans. Of the people that blame Congress, 58% are independents. Over here, 14% of the total people surveyed were Democrats. All right, so you just have to be very careful. First, identify if they are row or column percentages. Sometimes a chart or a table might say this, but other times it doesn't. You have to figure it out just based off the context of the chart. So let's look here at another cross-tabulation, this time between ideology, liberal, conservative, and partisanship, strong Democrat to strong Republican. Now, a lot of times people use these words interchangeably, which it's not true. Ideology is a different thing than partisanship. It just so happens that oftentimes in today's climate we see a lot of Democrats that are liberal, Republicans that are conservative. So let's see if there's a statistical relationship here. Well, the first thing to note is, we do see a cluster of people up here, and these are the people that are liberal to some degree and Democratic at some degree. We also see quite a few people down here, people that are Republican and conservative. So right there tells me there's something going on. Now, look at this. Are these row or column percentages? How would you interpret this 80%? So take a look and determine on your own if these are row or column percentages. So you find the 100%. 100% is over here. 80% of very liberal people identify as strong Democrats. These are row percentages. All right? And here again, based off percentages, you see this large group of people here and a large group of people over here. If you notice, there are 0% of the liberal individuals identify as any degree of Republican, and 0% of the people who say they're conservative identify as a Democrat to some degree. So it seems to be that there's a relationship there. But how can we test this association? Well, conveniently, there is a statistical test for this. This is known as a chi-square test. It's the uppercase chi with a square over it, hence chi-square. Essentially what we're doing, and it's much easier once I show you the example, we're comparing what we observe, our sample data, with a hypothetical table or chart of what might occur if there was no relationship. So if the two variables were totally independent, they did not influence each other at all, that would be one scenario. And then we're comparing that where there's no relationship with what we actually observe. And so we're comparing the two to see if there's a difference between what we would expect if there's no relationship and what we observe. So again, this is for looking at a relationship between variables, and it's especially helpful if we have nominal or ordinal level variables. But for a chi-square test, we still have a null hypothesis and an alternative hypothesis. Now, the chi-square test null hypothesis is that there is no relationship, or that the chi-square value is equal to 0. The alternative hypothesis is that the chi-square value is greater than 0. There's no negative here in this particular test. All right? So what we have to do is we take what we observe. This is exactly what we observed from our class survey. Frequency male, female, dog, cat. We need to figure out what would this distribution look like if there was no relationship between the two variables, if your gender had nothing to do with your favorite animal. And what we do is we need to calculate expected values. And there's a formula for this. I don't plan to ask you to do this, but you take the row total multiplied by the column total and divide by the total number of cases. So if I were to take the row total, 21, multiplied by 8, divided by 45, I would get this number, 3.7. And then for this one, 17.3 is what you get when you multiply 21 times 37 divided by 45. And so you calculate the expected values for all of this. All right? Again, the null hypothesis is that there's no relationship. So really, this is the no relationship. Sure, there's more people here than here, but that's a function of these these marginal values, 8 and 37. There's just more people that like dogs, and there's slightly more males than females. So this is what you would expect if there's no relationship, and this is what we actually see in our survey. Is there a statistical significant difference between what we observe and what we might expect if there's no relationship? So here's the case of the ideology and partisanship. We can calculate the expected values for each one of these cells. There will be a lot of calculations. We don't do this by hand. Computers can do this for us. And this is what the calculations look like. So here we have 6 times 5 divided by 43 is equal to 0.77. And here in this example, this red cell, 11 times 4 divided by 43. We do that for all of these values inside the box. All right? And then what we do is we take what we observe, subtracted by what we'd expect, and you do this for each cell. Again, so lots of calculations here. Square that and divide by what we expect for that cell. And by the time we sum all those up, we add up all these values, we get the number 201.8. This is our test statistic. Now, just like before, all we're going to do is compare our test statistic to the critical value. The only difference with a chi-square test is the distribution is a little bit different. This is what a chi-square distribution looks like. It is different from the normal distribution, and there's a table that you can find for critical values for a chi-square test. And so, just like before, how you read this table, here's the shaded region. And now here, there's a couple of new things. One, this tail probability. We want to be 95% confident, or we're willing to be wrong 5% of the time. So we're going to use this column. Now there's a new thing here. You may have seen it if you looked at the t distribution before, but sometimes in statistics we refer to a concept known as the degrees of freedom, or DF. Now, we don't really need to go into the logic behind this, but it basically has something to do with the number of variables you have and the number of cases that you have. So there's a formula for the chi-square test to calculate the degrees of freedom. You take the number of rows. In this case, we have 7 options for party identification. The number of columns, 7 options for ideology. 7 minus 1, 7 minus 1 is equal to 6 times 6 is 36. So follow the formula, 36 would be somewhere down here. The critical value is somewhere between 43 and 55. We can't tell exactly, but the point is, if that number, the critical value, is between 43 and 55, here's what we observe. This is our calculation of our test statistic. So if that's, say, 48, 201 is going to be all the way over here, way out here in the region of rejection. Hence, we can reject the null hypothesis and conclude that there is a significant relationship, we're 95% confident, between someone's ideology and their partisanship. All right? So just to review a little bit, again, lots of stuff going on here. Please feel free to go back, rewatch some of these sections, make sure that everything in your notes is good. Look up some things in the textbook, see if that helps you understand these concepts, because again, everything moving forward will add on to this. But we considered the standard normal distribution, and we learned about the difference between one and two-tailed tests. We learned about the different types of error. Specifically, we're interested in type 1 errors and the probability, or the p-value. We'll talk a little bit more about that, the probability of making a type 1 error. And we've decided we're willing to be wrong 5% of the time. And using that, we used the standard normal distribution, or just now we used the chi-square test to calculate what our critical values are. All right. Then we did some hypothesis testing. We learned the difference between a null and alternative hypothesis. We would test a sample mean against a population parameter. So those were the examples of the student newspaper, and making a claim that students study 4 hours a day, or that a particular politician is going to win 45% of the vote. And we tested these relationships between variables as well. So we did the difference of means, or a difference of proportions, and we also introduced the chi-square test. There's all sorts of other tests that do this. Your book talks about a couple more of these, but these are the ones that I really want you to focus on. And with all of these hypothesis tests, yes, there's different formulas. You can plug numbers into those. You can use your calculator, whatever it is. I'm not going to ask you to calculate these things. It's not really a math class. But the strategy is always to calculate that test statistic and compare it to the critical values. And then finally, we also did some point interval estimates. Essentially, we're using an estimate from our sample, and we're surrounding it with a confidence interval, right? The goal of all this is to take what we know about the sample and apply it to the population, draw inferences from what we know, the sample, and apply it to things that we don't know. All right, so please, again, just make sure that you have everything all squared away before moving on in the class.